Okay, so let us start by recalling what we did previously. So what we have seen what we saw last is the cut space, right? And the cuts themselves were these. Say we have a graph G whose vertex set is V and edge set is E. Then you consider a partition of the vertex set. A partition of V. Then what you do, you consider the set of all edges in G between V1 and V2. That is, any such edge has one of its end lying in V1 and the other end lying in V2. This denotes the set of all such edges in G. Such sets of edges, because this is after all going to be a set of edges in G, is called a cut or a co-cycle in G. And what we saw in the previous video is that together with the empty set considered as a subset of E, all the cuts in G form a subspace of the edge space of G, and that subspace we denote by C star, or to be more specific, C star of G. This is a subspace of the edge space of G, and this subspace we have called the cut space of G. And we have seen something else also, namely that if one of these partition sets is a singleton set, that it has only one vertex, then the other of course will be its complement. I mean, here also it's V2 and V1 are complements of each other, but here the complement is this. In this particular case also we can consider the corresponding cut, and this is generally denoted more simply by writing simply E of V, and it is just the set of all edges at V, that is, which are incident to V. And these special types of cuts in fact span the cut space or generate the cut space. Okay, so this is how far we have seen. So now today the author is going to show us what comes next, that is minimal cuts. So let's see what Diestel has to say, and then we will decipher every line. So he writes a minimal non-empty cut in G is called a bond. Okay, so that is the first thing, and then thus bonds in the cut space are what cycles are in the cycle space, that is the minimal elements. Okay, let us first try to understand this much. We understand the cut space. Now, what is being said here? A minimal non-empty cut in G is called a bond. We understand what cuts are. They are the sets of edges which look like this, right? There is a partition and all the edges in G running between the sets of that partition, they form one set of edges that is called a cut, and they are the vectors in the cut space. Okay. Now, minimality means what? Minimality means this. Say we are saying that a cut is minimal if you do not have another cut in the same graph that is properly contained in this cut, possibly with a different partition of the vertex set. This should not happen if this is minimal. That is, you will not get a proper subcut. Subcut I am saying, although I don't think there is anything called a subcut, but you can understand what I am trying to say here. The thing is that you should not get, if this is minimal, then you should not get another cut in the same graph which is properly contained as a subset of this set of edges. Yeah, that's what minimality means. So, minimality with respect to the containment relation. In an ordinary vector space, if you just say you are given any vector space. Now, in a vector space, if you take two vectors, do not confuse this V with this V, okay? This is just some vector space. Say you take two vectors V1 and V2, you cannot just simply say that V1 is greater than V2. You should have some order relation on the set of vectors in order to be able to say things like this. But due to the nature of our space where the vectors are sets, we already have a partial order, that is ordinary set containment, or the order of one set being a subset. So that's why we can talk about minimality. Okay. So in that sense, if you have a minimal cut, a minimal non-empty cut, that also has to be taken into account. The non-emptiness in G is called a bond. Okay, we are coming to that non-emptiness in the next line. But first let us see what the next line says, I mean this one. Thus bonds in the cut space are what cycles are in the cycle space. You remember the cycle space. Just like we have the cut space, which is a subspace of the edge space, we also have already seen the cycle space, which is spanned by all the cycles in G, or rather more specifically saying by the edges in the cycles in G. You take one cycle from the graph, you collect the set of edges, you take another cycle from the graph, you collect its set of edges. These sets of edges span a subspace of the edge space, that is the cycle, that was the cycle space. So in that cycle space, the cycles themselves, or rather their edges, are actually not all the vectors, they span. So the general vector in the cycle space is a linear combination of these cycles or the sets of edges. In the cut space, the difference is that the cuts themselves are the vectors along with the empty set, of course. So what role the bonds are playing in the cut space, that is being minimal in this respect, that same role is played by the cycles in the cycle space. That is, in the cycle space also the cycles are the minimal elements. You cannot get smaller than that in terms of this containment relation. Okay, so that is the minimum. Now next, note that the non-empty condition bites only if G is disconnected. Okay, now what is this? The non-empty condition only bites only if G is disconnected means it becomes a problem or is rather needed only in a disconnected graph. But why so? Say you have a disconnected graph, then it has at least two components. So what you can do is that you consider one component, you consider the other component, and whatever else is there, there may be more components, right? You consider those other components if they are present along with this component. Okay, and you keep this one component away. So because the graph is disconnected, you will have something here. I mean, apart from one component, you will have something else in the graph. So what you do is that you form this partition. Let V1 be the set of all the vertices present in this region, and V2 be the set of all the vertices present in this component. Okay, and then you consider the set of all edges running between V1 and V2. What will this set be? It will be the empty set. Right. Simply because the definition of component means between components there is no link. That's what component means. A component is a maximal connected subgraph in a graph. So that is why there is no edge between V1 and V2, but V1 and V2 are, of course, they form a partition of the entire vertex set, for which this set has become empty. Okay. Now if we do not take into account, or if we do not impose non-emptiness here, then for a disconnected graph, minimal bonds by definition being minimal cuts, there will be only one bond, which is this, and that's it. So the definition sort of becomes meaningless. So that is why, in order to keep bonds interesting, or in order to have bonds which are minimal but not this degenerate case, we need non-emptiness. So that's why the author writes, note that the non-empty condition bites only if G is disconnected. If G is connected, on the other hand, then something else happens. In that case, we do not need non-emptiness explicitly, although the minimal bonds being non-empty becomes just a consequence. Okay, so we are next coming to that. So the next line is this: if G is connected, I'm writing exactly what the author has written so that we can understand the meaning of each line. We do not want to miss anything. If G is connected, then in that case, then its bonds are just its minimal cuts. Do you know, do you see why? That is because any such cut you choose between two partition sets of vertices V1 and V2, it will not be empty, because if it is empty, then that means the graph has to be disconnected. There will be no edge joining any vertex of V1 to some vertex of V2. But that is not possible in a connected graph. So in a connected graph, if you seek minimality, the non-emptiness is there. Okay, so by definition, its bonds are just minimal cuts. You do not need non-emptiness separately. That's what the author is saying. But now the question is, how do we recognize these things, minimal cuts? And there is a way, and they are easy to recognize. A cut is minimal if and only, okay, let me first write the thing and then we will try to understand. If and only if the two parts, that is the two sets of vertices in that partition, they induce connected subgraphs. That is the condition. Clearly, we will make it clear. Clearly, a cut in a connected graph, why did I write non-empty? In a connected graph is minimal if and only if the partition sets, right? That's what, yeah, corresponding vertex partition induce connected subgraphs. Okay, that is, he has not written sets, but only if the corresponding vertex partition induces connected subgraphs. Okay, so now this is the way of recognizing if a cut is minimal or not. Now the first thing is, what does this mean? And the second thing is, how do we prove this? Or at least, how do we understand? The author, of course, has written clearly this is the case, but we need to understand how. So here's the thing. Say you have a cut. What he says is that and it's in a connected graph, okay. This is minimal if and only if the corresponding vertex partition induces connected subgraphs. So here is the thing. So this is one side of the partition, this is the other side. whatever vertices we have in V1, they are on this side, and those in V2 are on this side, and this is of course the set of edges which look like this, right? All the edges in G that are like this, they constitute this set, and that is our cut. So what this condition is saying is that the vertices in V1, they will induce a subgraph, right? If you consider those vertices and all the possible edges among them, then that gives you this induced subgraph in G induced by V1. Similarly, on this side you have an induced subgraph that is induced by V2. So this condition says that our cut is minimal if and only if both of these subgraphs are connected. Okay, this is connected, this is also connected, but how? That's the thing. So let's see. So let this be a cut. Let this be a minimal cut. Let's first see from this side. And suppose that say this is not connected. Okay, contrary to what is being said here, suppose this is not connected. Okay, so we have written our condition. Now we will try to arrive at a contradiction. And I am not writing here the things formally, I am just simply explaining. So I will again draw one such diagram. So the situation here is this. So we are supposing that this induced subgraph is not connected. That means there will be at least two components. If one of the components is C, then in the rest of the, I am not saying that the other, the rest of the graph itself is a component, but it will have at least something. Okay, so this is the rest of this subgraph GV1, induced subgraph. Now, okay, so keep in mind that we are in a connected graph. This whole thing is happening in a connected graph G, right? And there is no connection between this C and this. Okay. So that means whatever edges we originally have in this EV1, V2, they are like this. Okay. So that is these edges constitute this set EV1, V2. Now what we do, we consider another partition of the vertex. I mean, all the vertices of G are already here. Okay, that in fact we have the entire G here itself. So now what we do, we repartition the vertex set like this. So this is C, this is GV2, and GV1 of course we have, but since we are now going to do something else, I am not writing GV1. You understand what this is. This part is whatever we have in GV1 besides C. So now my partition is this. That is one set, I want to be specific, right? All the vertices on this part along with all the vertices here, they form one vertex set. That is my one set of the partition. Say that is V4, and the vertices in C form the other set of my partition. Okay. Now, the set of all edges between V3 and V4 is of course these edges that were already there in this part, that part. This is also a cut, right? Because we have a partition of the vertex set of G, and this is also a cut, means these edges form one set, that is a cut. But you can clearly see that this one, that is EV3, V4 is a proper subset of V1, V2. Why is it a subset? Because you can see that we are only considering this part from among all these edges. So it's a subset, and proper subset because we have lost some edges, at least one edge. And why have we lost at least one edge? That is because there must be some edges. Why should we have edges here? Why are there edges here in this part? That is because the graph is connected, and you should be able to come from here to this part because the original graph is connected, and the only way of doing that is to come around like this and then reach this place. And that's because we have supposed that GV1 itself is disconnected, and so there is no connection between this component and this component and the rest. Okay. So that is why there is at least one edge in this part. So we have lost one edge. That is the reason for having this proper contour length. But then the minimality of EV1, V2 is violated, and that is a contradiction. Because of this contradiction, our supposition is wrong. That is, GV1 cannot be disconnected. It has to be connected, and similarly GV2 also has to be connected. That means if our cut is minimal, then the partition sets induce connected subgraphs. That is one half of the claim. Now we go to the other half. Now the other half goes like this. Let be a cut in G such that these induced subgraphs are connected. Okay. Suppose we want to show that this is minimal. Suppose it's not minimal. Then I'm writing in short, okay, then there exists a partition V3, V4 of the vertex set for which the corresponding cut is properly contained in V1, V2. Okay. Now let's get rid of this part and start drawing things afresh. Okay, so now what is the situation? So this is our V1, this is our V2. So this is GV1, and we know that GV1 is connected. So there are no two parts or three parts there, it's just one connected subgraph in our original graph G. Similarly, GV2 is also connected, and whatever edges we have between these two parts are there, and they constitute this cut EV1, V2. But what we are saying is that there is a smaller, strictly smaller cut which is contained inside of this cut. So that means in order to obtain EV3, V4 from EV1, V2, you must remove at least one edge. Okay, and let such an edge be this. This edge is originally in EV1, V2, but it is not in EV3, V4. Right? Okay. Now, how do you okay, let me just, I lost the train of thought that I was following. So you remove this edge in order to get to this, or rather I should say that this edge is here but not present here. I forgot how I went from this one to this one. So what I remember is that if this edge is not present here, oh, okay, let us not forget one more thing. If you look at the definition of a cut, it is the set of all edges in G between V1 and V2, and this all is important. That means in considering a cut, actually we are not deleting any edge from the graph. That should be kept in mind. So although what I am saying here is that we get rid of one edge and then we get to this cut, I mean possibly deleting some other edges from EV1, V2, we at least have to delete one edge in getting this cut. From this cut, actually we are not deleting that edge from the graph. That edge somehow has to be made to vanish, but the only way of doing that is if you move either this vertex on this side or this vertex on this side, because then you do not consider this edge. You consider only the edges between these two parts. Now, if you move this vertex to this side and the edge now is not considered in EV3, V4, but that does what? It has consequences, because this is not the only thing that is happening. The thing is that you have other things here, right? Either you have some other thing here or you have something else here. Well, that actually creates one particular case in which you do not have anything else here other than this vertex and this vertex. We are coming to that afterwards. Okay, let us consider that we have something else here or something else here. Without losing generality, let's consider that we have something else here on this side. At least one other vertex. Now, the fact that you have considered GV2 to be connected forces you to have a path between this vertex and this vertex. So, when you move this vertex to this side, you cannot get rid of that path. Right? The path stays. And that path creates at least one edge again between these two parts. So you do not lose any edge. In your attempt to get rid of that edge, you actually have gotten another edge between these two parts. So there is no getting around this thing, that losing the number of edges does not come down. So that's why you cannot have one such subset which is properly contained in this, and because you keep in mind that we are dealing with finite graphs, so this kind of proper containment means that the number of edges in this set should be strictly less than the number of edges in this set. That we do not see happening here, and that is not possible also because all edges ultimately have to be there and we are actually not losing any edge. So it's impossible to take the number of edges down this way, and that is the only way you could possibly have removed this edge or made it vanish in this part. So that's why this is a contradiction. This kind of thing cannot be achieved if all these conditions are met, and that is a contradiction, because of which this supposition is wrong. That means this has to be minimal. So that's why the author says that a cut is minimal if and only if the two parts of the partition induce connected subgraphs, and that is the way of recognizing minimal cuts. Okay. That time that I forgot about what to do here, it had everything to do with this all. So you see how important every aspect of a definition is. If we forget that we must have ultimately all the edges, then it seems like we should actually just simply delete edges. That's not the case. Anyway, now moving on. And this next line, of course, is just obvious. If G is disconnected then its bonds are just the minimal cuts of its components. That is obvious. Okay, now why do we need bonds? You remember when we were studying the cycle space, there the cycles were the minimal elements, and they in fact, of course, by the definition of a cycle space, they span the cycle space, but in particular the smallest cycles, the chordless cycles, they also span the space. Now here, and in fact we found that the cycle space, in the cycle space, every vector is a disjoint union of chordless cycles. Now here the bonds are going to do something similar. So that is the next lemma. This is lemma 194. So let's see the statement. Every cut is a disjoint union of bonds. Of course, this statement says that the bonds span the cut space, but it says more, right? That every vector in the cut space, that is every cut, is in fact a disjoint union of bonds. So let's now see the proof. Okay, but before I need a little ink. I forgot to refill it. Just give me a moment. Okay, so in the beginning of the proof, we go through a little something. Let's see what it is, and then we start the proof proper. So here's the thing. Let H equal to V comma E be a connected graph C, which is a subgraph of H, be a connected subgraph. We are specifically mentioning that C is a connected subgraph because in a connected graph you can consider a disconnected subgraph, but C is a connected subgraph. And let D be a component of H minus C. And the situation here is of course expressed in the form of a diagram by the author like this. So this is our C, and there are some connections like this, and this is D. The entirety is H. Okay, so what we have here is a connected graph H and a connected subgraph C of H. C is not, although it looks like this, but C is not necessarily a component in, okay, it cannot be a component, right? I mean, what I am trying to say is that because H is connected, H itself is its only component, in that C is just a connected subgraph. Now, if you remove C from H, then you will be left with something. Oh, I think I forgot to do one thing, no? I mean, in showing that this, I totally forgot it. In this situation where these are connected, we were showing that this is minimal, right? But we left out this case where you have only this and this and nothing else. That means in V1 you have just only one vertex, and in V2 you have another vertex. So what we were trying to show, it is given that these two are connected. Let me just postpone this for a moment. We need to complete this, right? So what we supposed is that this is not connected. That means, this is not minimal. So that means there is something like this. But again, just like what we saw over there, you need to move this to this side in order to make that happen. But if you do that in this case, you are not left with anything on this side. So in order to lose this H, you have to consider both of its ends in one partition set. But that's all we have. The other partition set, whether you want to call it V4 or V3, does not matter, becomes empty, but then it is not a partition. So that itself gives us a contradiction. So that cannot be done. So in this case also, this cannot happen. Such an EV3, V4 cannot exist. So because of which it has to be minimal. Okay, so now let us continue with this one. So if we take out this C from H, then we are left with something, and in that something, this D is a component. D may be the only component, right? These other places may not exist, but at least D is there. Now, in this situation, what can be said about this next thing? Then the author writes, then H minus D2 is connected, so the edges between D and H minus D form a minimal cut. Okay, so now what is happening here? Then he writes, if this is the situation, then H minus D2 is connected. If instead of removing C from H, say you remove D from H, then H minus D is this rest, whatever is left. This is our H minus D. Why is that connected? Because if it is not connected, then our original H would not be connected. And why is that so? That is because if H minus D is not connected, then that means you have at least two connected components here. But then those two components cannot be made connected if you bring back D. Why? Because the edges that you lost when you removed D have nothing to do with what is happening in this part. So that's why H minus D has to be connected, right? But then what do we get? You see, you are looking at the entire H, entire graph H, in which you now have a partition of two sets. Partition of the vertex set. One half has the vertices lying on this side and the other half is the vertices in D, and you have the edges between those two vertex partition sets. This part is connected, H minus D, that's what we have concluded just now, and D being a component is of course itself connected. It's a connected subgraph of H. But we have already seen that when that happens, that on the two sides connected subgraphs are induced, then this becomes a minimal cut. So that's what we have written. So the edges between D and H minus D form a minimal cut when this happens. And by the choice of D, because of how D has been chosen, it's a component of H minus C, this cut is precisely the set E, C, comma D. But why between C and D only? That's because just what we have seen now, these edges have nothing to do with the rest of H minus D. It only links C with D. That's why those edges will only form this cut, and this is a minimal cut of all C minus D edges, of all CD edges, of all CD edges in H. CD edges means those edges whose one end lies in C and the other end lies in D. Okay. Now actually the proof starts. So this is something that we have seen, it happens. Now this will be used in the proof. Okay, so next what the author writes is this: to prove the lemma, we are going to consider an arbitrary cut in a connected, in a graph. Let a cut in an arbitrary graph G equal to V, E be given or be considered with, that means the partition has to be mentioned, this of V, say. Okay, so that means what is given? Such a cut is given means an arbitrary vector is given in the cut space. Now we need to show that this vector is a disjoint union of bonds in the graph. Okay. Now consider a component C of GV1. We have the induced subgraph in G by the vertex at V1. Whatever it is, it will have at least one component, right? And let C be one such component. We have chosen one component. And let H be a component of G containing C. Our original G may be disconnected, but because we have this component C, we can consider a component H in G that will have this component C as a subgraph. Okay, so that will always be there. If you cannot see how, you just think of it. Keep in mind that this component C is a component in this induced subgraph GV1, whereas the component H is a component in the original graph G, and for a C we will always have one such H. This part I am leaving to you to understand how and why. Okay. Then it's not very difficult to understand why. Okay, then what happens? Then E C comma V2, which is also E C comma H minus C, is the disjoint union of all the H sets H sets which look like this, C comma D, where D is a component in the induced subgraph by V2, that is GV2. Over all the components, B of H minus C. Okay, now what is it that we are now saying here? So what is happening is this. On this side we have some other things. Okay, so this is perhaps I should have had more space, but anyway, this is V1 and this is V2. You understand that this part is V1 and this part is V2. Because we don't know whether these parts induce connected subgraphs or not, so we have drawn multiple components in those induced subgraphs. This part, whatever subgraph this part induces, that is induced by V1, has these components. Like that, GV2 has these components. And one of those components is our C. Consider a component C of GV1. So say that component is this C. And let H be a component of G containing C. Of course, H will be there somewhere in G, which contains this component C. And H, being a component of G, will be a connected graph. And that's how we started our proof. Remember, in the beginning of the proof, we considered a connected graph H and a component C of H. Okay, so H is here somewhere, right? So now what we are saying is that, okay, so from that, this looks awful. Let me just draw it on this side instead, taking more space, because this is looking just simply cluttered and clumsy. It's looking extremely bad. I should write on this side, and let me draw it here. This of course does not mean that each side has 4 components. I am just simply showing 4. This is GV1 and that is GV2. This is C and we have H. Now, because we do not know whether H will lie only on this side, we do not know. So we have just simply drawn H like this, a little to cover that side also. So this is H. Okay, so what is happening here? C is a component of this induced subgraph GV1. Okay. H is a component in the original graph G that contains C, and it has been left to you to convince yourself that such an H exists. Okay, that part is left to you. Now what we are saying is that this set of edges, that means all the edges between C and V2, there may be many such edges like these, many such edges may be there. Okay, and which is just simply the set of all edges between C and H minus C. Okay, now here is the thing. How is this V2, I mean all edges between C and V2 suddenly becomes all edges between C and H minus C? That is because if say this component is something outside H, say this component has one vertex, say V, which is not a vertex in the subgraph H. Okay, then is that possible? I mean, then shall we have a connection between some vertex of C and this vertex? Actually no, because otherwise that thing would have been present here itself. Why? That's because H is a component in G. So by definition it's a connected subgraph of G. You cannot have something else coming from outside which has no connection with H suddenly having a connection with one part of H. Okay, because otherwise this would have been a part of H itself. By the definition of a component, it's a maximal connected subgraph. So if there is a connection, it will be engulfed by H itself. Okay, so that is why whenever you are considering edges between C and V2, actually you are considering edges between C and H minus C. So whatever is happening will happen from within H itself. So if there are connections like this, then they will be inside H itself. So that's why we write C H minus C. And what else we are writing? That this set is the disjoint union of all the H sets E C comma D over all the components D of H minus C. So for example, this is say one D, say D1. This is another component D2. This is another component D3. And it is clear why is this H set disjoint union. That is because between two different components, if you see the connections, there can be no common edge naturally, because components by definition themselves do not have any common vertex. So whatever connections we will have, they are going to be disjoint. All these edges and these edges, there can be no common edge. Similarly, these edges and these edges are all going to form disjoint sets of edges, right? And this entire set of such edges, which is this set, is going to be the disjoint union of all edge sets when you consider these components of H minus C. When you take C, when you remove C from H, whatever components are left, all these connections, they will be disjoint and together they will give this set C. But in the beginning of the proof, we have seen that such connections, when considered in chunks, they form minimal cuts. That's what we saw, right? That's why we are using this notation C, H and D. You go to the beginning of the proof and you see that. So that's why next the author writes, by our earlier considerations, these are minimal cuts or bonds. These sets are minimal cuts in H. And hence bonds in G. Keep in mind our original G may be disconnected, but according to what we have seen about the about bonds, if G is disconnected, then the bonds are just the minimal cuts in the components, and H is one such component in which these are the minimal cuts. These edges form one minimal cut, these edges form another minimal cut, these edges form another minimal cut. So each one of them is a bond, and this set of edges between C and the rest of H or the rest of the graph itself, I mean apart from this side, that side, that is a disjoint union of these bonds, which you can just simply see. It's the union of these edges and they are disjoint. But now next what we do, we vary this C also. That is, instead of considering only this component, you next consider similarly the other components also. And that's just it. That is going to give you all the possible edges between this side and that side. And you can clearly see that when you do that, then also this disjointness of the bonds, and or rather I should say the disjointness of the union of the bonds, and the fact that you are in fact going to consider all the edges between this part and that part, that becomes clear. So that's the next thing the author writes. Now the disjoint union of all the edges in how is it he writing this? All these edge sets, all the edge sets in is C, V2. Yeah, we can write that because that's how we started now. Taken over all the components C of GV1. Is precisely the cut if V1, V2. So you now it becomes absolutely clear what is happening. You have V1, you have V2, you consider the components on this side separately, you consider the components on that side separately. You take any component from this side, you take any component from that side, from these induced subgraphs, and then you consider the edges between those two components, one on this side and one on that side. Those edges form a bond, and when you collect all such bonds, then this cut, that is the set of all edges between this and that part, that becomes a disjoint union of these bonds. That's it. So that's why the bonds span the cut space. Okay, they generate the vector space consisting of all the cuts along with the empty set, and that is the end of this proof. Now you have the cut space and you have the cycled space. In the next result that we will do in the next video, you will see that they are a sort of orthogonal complements of each other, where the orthogonality will come from that inner product like thing we have defined in this situation, right? From there the orthogonality relation will come. So these things we will see in the next graph theory update. So let me end things here itself, and tomorrow is Saturday. So last Saturday we solved Gallian's group theory problems. So tomorrow let us solve Gallian's ring theory problems. So with that I end things, and so see you tomorrow with Gallian's ring problems. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.